Thank you for the introduction. It's a pleasure to be here today. We begin by saying, what are the key requirements of medical staff from a water treatment system? For the physicians, it's uninterrupted treatment to patients with high quality water according to the international standards, AMI and EC standards. For the nurses, of course, it's a system which is easy to use, saving more time for the patients, for the patient treatments. And for the technicians, it's a smartly designed system, mainly where it can be easily maintained, and the disinfection process is also a simplified process. In today's presentation, basically, I will present to you the evolution of the water treatment system for hemodialysis, leading up to the most recent designs. And along the way, I will highlight the disadvantage of the older design and the advantage of the newer designs. Before we go into this, though, we have to understand a bit the basics of the water treatment. So as we see here, this consists of the entire system itself. The key step in the treatment process is the reverse osmosis, which basically filters out everything on an ionic level and above. So we're talking about microorganisms, bacteria, fungi, viruses, and of course it removes all the minerals and salts, essentially bringing it to the level of required by the international standards for dialysis water. So one stream is the purified water and one stream is sent to drain. All the steps before, what we see is what we call the pre-treatment. It's essentially priming the water so we get it ready to be suitable for the main step in the treatment, so that first of all, we prolong the lifetime of the RO membranes and we delay the development of microorganisms. Something to keep from this is that the pre-treatment steps, so we have turbidity filter, which removes the suspended solids from there, the softener, which removes the hardness from the water, the automatic carbon filter, which removes the chlorine, which is in the water, and also any organic content, and the 5-micron cartridge filter, which removes anything above 5 micron, basically making the system ready for the RO system step. So let's look at the first and the oldest design. The oldest design, we have a single pre-treatment and one RO unit. The purified water is collected in a purified water tank, and from there it's pumped via a UV system, a microbial cartridge filter, so it's disinfected so it can be suitable for the hemodialysis machines. The water which is not used is returned back to the purified water tank. In regards to the disinfection which may be needed for the membranes, the RO system, since we have development of microbes there, as well as the distribution ring, it's done by chemical disinfection. What are the issues now with this design? First of all, we have the water treated by one RO, so essentially we do have purified water, but it is rarely ultra pure. So depending on the source of water that you have, if let's say you have high levels of minerals, you may be very close to the limits set by the international standards. Second of all, you don't have any backup equipment. So there's no redundancy in the pre-treatment. There's only one RO. So in case of failure or stoppage of any system, there will be interruption to the water supply to the hemodialysis beds. What does this mean? We're obliged to have a purified water tank. And this purified water tank essentially must be sized to cover at least one hemodialysis shift. The issues with the purified water tank, though, is that it's a source of microbial growth. Stagnant water leads to microbial growth. Additional steps of treatment is required downstream, so you need a microbial filter and a UV system. Of course, these are disinfectant steps, but the hydraulic equipment itself on the loop may be a source of microorganism growth. And lastly, also the purified water tank has to be usually a minimum of 2,000 liters in capacity, so you have a larger plant footprint. The disadvantage of chemical disinfection. First and foremost, of course, residual chemicals. The presence of residual chemicals can pose a health risk to patients undergoing dialysis, so several flushing and testing is required to ensure it is within safe limits. Rarely does it pose a risk that the chemical remains in the loop, but it's more of the time consumed to actually flush it out successfully. Second of all, it is a manual procedure, and it's a time-consuming procedure. It's not an automated process, but it requires a biomedical technician to add the chemicals to be present during the disinfection process and all the procedure required later on. It's also a costly step, a process. It requires the regular purchase of chemicals. It consumes large amounts of water for effectively disinfecting and flushing out of the ring. Of course, you have all the difficulties to store and handle the chemicals. And finally, it's been shown that, okay, it may be effective, but sometimes you may require very high concentrations of the chemicals. And also against biofilm, it has been shown to not be as effective as hot water, which we'll see a bit later on. Chronologically, then the next step in the design was essentially as we saw previously, but what we had was 2 ROs in series. The improvement here essentially is only the fact that we have 2 RO in series, so we were producing ultra-pure water quality. So we covered the issue that we faced with the fluctuating feed water quality. However, all the other issues remained, that we required a purified water tank. Why? Because the RO itself, even though we have 2 RO in series, and each RO is capable to provide the quality and the quantity, if one stopped or failed, it required manual intervention to have the other RO in operation. So this meant the system had to stop, and you still required the purified water tank. Also, we did not have any redundancy in the pretreatment. The other issue that remained in this design was that we still had chemical disinfection. The third design chronologically was an improvement to the previous one, was a double pass RO and online. What we see here is we have complete redundancy and backup in the pretreatment. So we have 2 of each, 2 feed pumps, 2 sand filters, softeners, active carbon filters, and 5 micron filters. And most importantly is that the RO system 2 in series have a feature which is an automatic immediate switchover. So that if one RO fails, automatically and immediately the other RO takes effect and sends the required water online. It is not to ultra-pure standard, but it's still within the international limits. So it's an online system. However, the only setback here is that the disinfection of the RO system and the distribution ring was done with chemicals. This is what we discussed now. We come to the most recent and the newest, let's say, design that we have in the field now. This is essentially the same philosophy as the previous one, but the difference is that the disinfection is performed with hot water, both for the distribution ring and for the RO, and both together. So we have full redundancy in the pretreatment, we have 2 RO in series, and the addition here is that we have a hot water disinfection tank. Since disinfection is performed with hot water, and for the RO system, and for the loop, we have to have special materials here. So the RO, which we'll discuss in more detail a bit further down, has to be from stainless steel, and the membranes are specialized membranes which can withstand the high temperatures. So the general process is that, very simply, when we're comparing it in relation to the chemical disinfection, with the press of one button, the operator and the biomed technician just chooses what type of disinfection he wants to perform. So this could be the distribution ring, the RO, or both together. By the press of one button, purified water enters the hot water disinfection tank. Once it's full, it starts heating up to reach a temperature of 8 to 85 degrees, whatever has been already set before. Once the temperature is reached, the pump then will send the water to the distribution ring, or to the RO if it has been set accordingly. Once the disinfection is completed, all the hot water is collected in the tank to cool down, and then it's sent to drain. It's a very simple process without the addition of any chemicals. What's the advantage of hot water disinfection technology? First of all, it's a highly effective at killing or deactivating microorganisms, delivering consistently lower bacterial and toxin counts. It's very effective at removing and preventing biofilm formation both in the membranes and in the distribution ring. Third, it's been shown to be more effective at removal of silica from the RO membranes. Fourth, and important, is that it eliminates the possibility of introduction of chemicals, improving the patient safety. Fifth is that there's labor savings. It's a completely automated process, so it's just a press of a button, and it's an automated procedure, so it replaces the otherwise manual procedure with chemicals, reducing staff labor hours. I think one of the most important points here is that it improves the performance because you can perform more regular disinfections since it's such an easy procedure. So you can perform more preventive maintenance and disinfection in comparison to chemical disinfection. It's also eco-friendly. You have less water consumption as multiple flushing to remove chemical residue would otherwise be needed. And also there's no chemicals disposed into the sewer. Also, it's a cost-effective solution. It eliminates the purchase and handling of chemicals and less water consumption. At this point, I'd like to introduce to you the Temac TMED 2 Series Hot, which encompasses the design and all the features of the latest design that I just discussed. And in addition, I will also highlight some additional features, and we can look into some of the design features of the system. So this is what we said before. It's a duplex pretreatment. So if one fails, the other one can continue to treat the water without stoppage of the system. The pretreatment on a daily basis has either backwashing of the filters or regeneration of the softeners. So if backwashing or regeneration occurs during operation, the other one can continue to treat the water without stoppage of the system. And this is critical in the case that you want to operate the system all day long or in emergency cases. The way that we design the system is that although we have two of each of the pretreatment steps, we send the water to be filtered in parallel so that we avoid any stagnancy. We also size the softener so that it is able to handle one entire day's operation, so 4 shifts, without interruption of the water, in the case that the other softener is offline. The reverse osmosis system itself. It's a double pass in series operation, so of course when both are operating, you are producing ultra pure water. It's got what we mentioned before, the automatic bypass, so in case that one of the two RO fails, the other one automatically takes over and supplies the water to the distribution ring. We have hot sanitizable membranes. The entire skid from the RO onwards is manufactured with 316L with special roughness. This is necessary to withstand the high temperatures during hot sanitization. And of course, the 316L with special roughness to pharmaceutical standard is also necessary to reduce the buildup of microorganisms due to the smoothness of the stainless steel. So this is just an indication of what it looks like. Here we also are using 316L hygienic tri-clamp connections. This is a dead-end free design because we don't have any threaded connections, which are a source for buildup of debris and contaminants and microorganisms. Also, it's a useful feature for maintenance purposes because you can easily connect and disconnect it. The hot water sanitization system consists of a hot water tank. Usually the capacity is 300 to 500 liters. This is also with special roughness against microbial growth. You have the microbial air filter to filter out any microbes entering the tank. The tank itself is double-walled to avoid any heat dissipating and protection of the users. You have the hot water distribution pump, which sends the water either to the distribution ring or to the RO membranes. And in the PLC, as I mentioned earlier, a single button operation for the disinfection either of the RO, of the distribution ring, or both together. PLC automation. It's a fully automatic process. No manual intervention is required here. The control panels are easy to use and service. We have also a feature which is an automatic periodical flushing feature that is necessary that when the system stopped, we set a specific time, let's say after 4 hours of stoppage, it will operate for 15 minutes to circulate the water so we avoid any stagnancy. Another feature in our design is that each of the 2 RO skids, each one has its own dedicated control panel. And we also have, for the hot water disinfection system, another dedicated PLC control panel. This allows for full redundancy compared to having a central PLC, which in this case, in the case of failure, the complete system would shut down. As TEMAC, we have installed more than 150 water treatment systems for dialysis in Greece and internationally. More from the conventional. Regarding the more recent design that I just presented today, these are some indicative references. One in Sultanate of Oman, Masiro Hospital. The production was 800 liters per hour, suitable for 11 hemodialysis beds. In Sinas Polyclinic, Sultanate of Oman, 1,600 liters per hour, suitable for 22 beds. In Amiri Hospital in Kuwait, 1,500 liters per hour, suitable for 20 hemodialysis beds. In Venizelos Hospital, we have 2 installations in Greece. The production is 1,500 liters per hour, suitable for 20 beds. And last is in BANTAO A Hospital, under the supervision of Dr. Grapsa. The production is 900 liters per hour, and the hemodialysis beds is for 13.